Welcome. Today we're going to learn about the electric field. In learning about the electric field, we're going to learn about electric field lines, the shape of electric fields, and the force on a point charge due to an electric field. Before we do that though, you should remember that the Coulomb force between two charged particles is given by the Coulomb constant K times the product of the two charges divided by their distance squared, and it's directed along a line that connects the two charges. Now you're probably wondering and have been dying to ask, how do charged particles know to exert forces on other charged particles? Well, that's a good question because charged particles don't need to touch in order to exert forces on each other. So how do they know to push or pull on another charged particle? How does a negative charge know to repel another negative charge? How does a positive charge know to repel another positive charge? Yet if you put a negative and a positive together, how do they even know they're negative and positive and know to exert attractive forces on each other? Well, the answer lies in the electric field. An electric field is the mechanism through which electric force is communicated between two charged particles. It is a model. But it's a model used to describe the alteration of space itself surrounding a charged particle due to its charge. So in other words, an electric field influences the space around it. So I said the electric field communicates. It is the mechanism through which charged particles communicate. Think of it like this. Imagine you're somewhere out hiking. You're having a nice day, but you're feeling kind of lonely. So because you're feeling kind of lonely, you put out a message. Hey, is anyone there? Now, because you yell it, that message spreads out in space. And it keeps spreading out. And that message goes on. And even though the message might be getting fainter the farther away it goes, it's still out there. Hey, is anyone there? And now you're waiting for a response. You're listening. Now, if someone happened to be out there with you and heard your message, they might be responding to you. They might be saying, I'm here. And when they yell that out, their message spreads out in space as well. And eventually you hear it. I'm here. Now the electric field isn't too dissimilar from this. Surrounding every charged particle is an electric field that completely fills the space around it. The electric field is a messenger, kind of like this example of you out there putting out a message. But the electric field communicates more than, is anyone there? The electric field's message would be something like this. I'm a positive particle. And that message goes on into space. And I'm here. Now, someone else might be out in space and they might not have heard your message yet. But because they're out in space too, they're constantly sending a message. I'm here. And I'm negative. So that person communicates what they are, where they are. You communicate what you are, where you are. Your messages are like the electric field. Now, you don't need another person for you to say, hey, is anyone out there? I'm here and I'm positive. You don't need anyone else in space to hear that message, but you're still going to send it. The electric field is like that. Let's say we have that positive charge. At every point in space completely surrounding this positive charge, there is an electric field vector at that point. That electric field vector has a specific magnitude and it acts in a specific direction. I can spend a long time drawing hundreds, then thousands, then millions of electric field vectors. However, it would take an infinite amount of time to draw the infinite number of electric field vectors that completely surround this positive charge in space. And the reason why that is, there are an infinite number of points in space. So I could really only draw a finite number of points. However, I know that at each point, for that specific charge, there is going to be one and only one value of its electric field at that point. And that value of the electric field for that charge at that point is going to have a specific magnitude. We use the variable E to represent electric field. And being a vector, the electric field has a specific magnitude and a specific direction at every point in space for this charged particle. The strength of the electric field diminishes with distance. You will see that it follows an inverse square law for point charges. If I just drew a few representative vectors, and this certainly isn't to scale, we see that the electric field is diminishing in magnitude in space. Any charge that we place in an external electric field will experience a force due to that field. Let's place another positive charge somewhere in this electric field. I'll place another positive charge right here. That positive charge is experiencing a repulsive force from the electric field produced by the other positive charge. That repulsive force is in the direction of the electric field vector at that point. So this field vector right here at this point, at that point, that charge is going to experience a force. And that force is going to be in the direction of the electric field. This will be the force of repulsion between those two positive charges at that point due to the electric field at that point. If we move the positive charge to be closer, we know from Coulomb's law that the electric force will be greater. So the electric force at that point, I'll just go ahead and call this point 1, and I will call this further point, point 2. The electric force at that point is due to the electric field at that point. So the electric force at point 1 is due to the electric field at point 1. The electric force at point 2 is due to the electric field at point 2. What we'll see here is that the force of interaction due to the electric field is directly proportional to the electric field. And rather, since we're just learning about the electric field, let's say the electric field is directly proportional to the electric force. You might be wondering what the constant of proportionality is. Well, let's identify these charges. I'm going to call the charge in the middle, the one that's producing the electric field that we're interested in, Q. I'm going to call this charge that we placed in the field Q naught. Q naught will be our test charge. The reason why I'm calling it a test charge is we're going to use a very, very tiny positive charge to probe the electric field in the space around any area we're interested in. By convention, we call this a test charge, and this test charge is just a very small positive charge. The reason why we choose a positive test charge is if we know that our test charge is positive, and if we know it's experiencing a force in a particular direction, we can then determine the magnitude and direction of the electric field at that point. So what is the constant of proportionality between the electric field and the force caused by the electric field? The constant of proportionality is the charge that we put in the field. This actually defines the electric field for us. The electric field is the force per unit charge acting at a point in space.